Okay, so hi everyone, Senan this side, and in this video we are going to solve this lead code daily problem. So this is 12:46 a.m. and we are going to solve this problem, deletion and reverse in circular linked list. So before we get started, I just want you guys to know the whole PDF solution is provided in the description below, where you can check out the GitHub link and directly get this PDF solution for free with my C++ code and the intuition approach, the time and space complexity, and the code again. So let's get started. And in this one, I did something which I don't think I have ever used before in any of the questions. So let's see that. Okay, so the question is asking deletion and reverse in circular linked list. So given a circular linked list, the task is to delete the given node key in the circular linked list and reverse the circular linked list. So basically you have to write two functions that reverses and deletes a node. You don't have to print anything, just return the head of the modified list in each function. Fine. Now let's look at the test cases for what exactly it is looking. Given a linked list like let's say 2, 5, 7, 8 and 10, the key is 8. And what you have to do is you have to first delete this 8. So you'll get a list 2, 5, 7, 10, and since it is a circular linked list, it goes back to 2. Now what you do is you perform this reverse operation so that 2, 5, 7 and 10 to 2 goes to 10, 7, 5, 2, and that again goes back to 10. Although that is not shown here, but the link goes back from 2 to 10. Similarly, in this case, 1, 7, 8 and 10, you remove 8, so 1, 7, 10, and then you reverse the linked list, so 10, 7 and 1. Okay, so expected time complexity is this, and which is what we are going to meet. Okay, so the element is in this range, so I don't think there is any problem using an integer. Similarly, number of nodes is greater than equal to 2. Although in my solution I have taken the case where number of nodes is 0, 1 and this range, just so that you get an idea or a feel of what exactly you have to do, because that is one of the possible edge cases. Okay, so the reversing process is exactly same as you do in a normal linked list, just a couple of things. If head is null, that means there is no circular linked list to reverse, so I return null. So I am assuming the head is, if it is null, this property is holding vacuously. Now, okay, so what we did in a singly linked list, you took a current and you took a previous and you updated till you reach either the null, either till the time the current reaches null, right? That is how you did it in singly linked list, and there is a video on my channel, you can find that. But what I do in this case is I assign this previous and this current, this previous as head and this current as heads next. Now if current is not equal to head, right, current is heads next, right? So if it is not equal to head, what do, you get the next node, you assign this, reassign this link, you update the previous and current. So this step is exactly what you do in a singly linked list. What thing that is differing here is this line and this initialization. Okay, so in that you initialize that current to head and previous to null, and you only performed this operation when previous, the not exactly this operation, the different operation, when previous is not null, you do perform a sum operation. But in this case you assign previous to head and current is heads next. Now you check the while loop. Now the thing is, how do you detect that you have cycled through the list at least once or exactly once, right? Because this is a circular linked list, you can go on and on and on and you won't ever stop. So the stopping condition is when current is equal to head. That is the stopping condition. So initially current is heads next. So if current is equal to head, that means I have looked at all the elements in that linked list. So that is the way I determine that I have seen every element exactly once. Now in the end, what I do is when you reassign the links, right? So for example, if I do a short dry run of this list, we have 2 goes to 5 goes to 7 goes to, let's say, 10 after deletion, and 10 this actually goes to 2, which is this first one. So let me denote this in a bracket that this is a link, this arrow goes back to this 2. Now we have to reverse the list, right? So this is, let's call this 2 as previous, and let's call this 2 as previous and 5 as the current. Now what I do is I say that I keep track of this next, which is 7, and current's next is what? Current's next is previous. So I change this link to this one and I remove this link. Let's just separate this by a comma. Now we have next, right? Next is 7. So I say previous is 5 and the current is this 7. Now what I do is I take this link, I remove this, I reassign this link at this position. Again, what I do is this is previous, this is 10 is current. I reassign the link and just that. And now this is my previous, right? After this iteration is over, this was my current. So now this becomes my previous, and the current is what? Current is actually my head. So current is this head and this is the previous. Now you see we have reassigned all the or reassigned the links, but the only link that is remaining is from this head, right? This head is also actually pointing to this 5 as well, or in other way, this link is bi-directional. So initially I did a mistake, so I had to reassign the link of 5, not the link of the 2 is having a bi-directional link from 2 to 5 and 5 to 2. So since this head is 2, what I do is take this head and assign that next to this previous. So now I remove this link from here and I assign this to what? I assign this to 10 and I remove this. So now we have reversed the list. So that was the idea, a simple short dry run. I should not have explained that one, but the idea is exactly the same as you do in a single linked list. Just you have to, rather than assigning the previous is next as null, what you do is you do this heads next is actually previous. Now reverse was straightforward. The time and space complexity is constant. Time complexity is big O of n, where n is the number of elements in the linked list, and because we're using a while loop, right, we have to iterate through the whole. So yep, we are done with this reverse, and now let's look at this lead node. And one thing I did in this, I really think that I have used a do while loop for the very first time in a problem, or or in a long time. I've never used a do while loop as far as I can remember. I might have, I don't remember. Now the first two cases, let's say if head is null, you return null, assuming it holds true vacuously. Now the next case is, let's say your linked list, circular linked list, has a single element that is pointing to itself. So if head is equal to heads next, that is, it's pointing to itself. That means it has a single node and the data is this key of this head. What you do is you delete this head and you return null because there is exactly a single element there. Okay, although given this test cases constraint, you won't have to even check these two if statements, but just for someone who is curious. Now what I do, I initialize this current to head and I do this like while current is not equal to head. So I wanted to start at the head, but my while loop is not equal to head. So I at least want to go into this while loop one time, and that is why I use do while loop. So what I say is, I in this do while loop, what I'm trying to do is basically iterate through the list, right? And now if the data is equal to key, so I am at a node, right, which needs to be deleted. Now when you have to delete a node, what do you do exactly? You try to get the node previous to it, and then at a node, let's say if you want to delete this 7, what do? To delete the 7, you first go to 10 and you save this node, you reassign this 10 to 7 link to 10 to 1 link, and then delete the 7th. That is exactly what you do. Since let's say you are at a position which is the head itself, right, and you have to delete that node. So to get the previous of head, like in this case, if you want to get previous of 1, which is 10, you cannot directly get this from 1 itself. What you have to do is traverse this to 7, 8, 10, and 1. And when you see from this 10 you reach this one, at that point of time you know that the previous of head is this 10. But for searching, we are going to do a constant time deletion given at a node. So what you do, let's say the idea is this. So before that, when you find an element or the data that you have to delete, you delete that node and you break out of that loop, and in the end you return the head. So this is the basic general idea. You clearly understand. Now allow me to explain these three statements. Now let's say I am at this seventh node, right? Or I am at this first node, but I don't know the previous of one, which is the head, right? I don't know previous of head. So what I do is I try to be a bit clever. What I do is I swap this 1 and 7. This swap, the very first line, I swap the data 1 and 7. So my new list is 7, 1, 8, 10, 7, 1, 8, 10, 7, 1, 8, 10. Now, since now 7 is here and I'm already at this position, now I can just directly delete this node. How? I store this node 1. I say 7's next is 1's next, which is 7's next is 8, and I just delete this node. So now I just do the reassigning the links, storing that the next node, reassigning the links, and then deleting this node. So what I'm doing is actually reassigning the data in the nodes itself. So that is easy, right? So rather than finding the previous of this, I had to traverse the whole linked list. I don't have to do that anymore. I can just get this node, swap the data with the next value, delete the next node, and reassign the links. Or basically reassign the links, then deleting the node. That is what you do. So this is the whole idea for deletion. Now let me go over this very briefly. This is the edge cases for no node or a single node, which won't be the case because the constraints are like that. Now I take this current, I find if the data in this current needs to be deleted. I swap the data with the element next to it, delete that element, reassign the links. And I do this, I traverse this, and whenever I find this data is equal to key, I break out of this loop and in the end return the head. So yep, that was the whole video. In this case, the time and space complexity is what? Space complexity is constant because we are just declaring a few nodes and nothing else, like this node and this node, this temp. The time complexity is big O of n because we are traversing this loop, and this is a constant time operation. So is this. So this is big O of n time and big O of 1 space. Same for both, and this is the whole video. Let me go through my document once to see if I'm not missing anything. Okay, so the intuition is pretty clear. Reversing and deletion, time and space complexity big O of n, and space is big O of 1 for both of them. This is the same code that I've given with a few comments. And yep, thanks for watching, and I'll see you in the next one.